In this video, we're going to look at the concept of internal energy. Pause the video to do these questions. Press play once you've done them. You should have now done these three questions. I'm going to go through them. Please mark and correct as I go through them. So if you've got a substance in the gas state, the particles will be moving faster than in the solid state, and therefore the kinetic energy of the particles in the gas state is higher than the kinetic energy of the particles in the solid state. So the kinetic energy of the particles in the gas state is bigger than the kinetic energy of the particles in the solid state. So particles in a gas move faster than particles in a solid. In fact, the particles in the solid just vibrate on the spot. They don't move around freely. Question 2, the forces of attraction. So the forces of attraction are strongest in a solid, then in a liquid, and then in a gas they're weakest, almost non-existent in fact. So the particles in the solid state have greater forces of attraction. So the forces of attraction in the solid state are bigger than the forces of attraction in the liquid state. Finally, how can the elastic potential energy store of a spring be increased? Stretching the spring, or if the spring can be squashed, squashing it will also increase the elastic potential energy, but generally it would be through stretching it. So by stretching the spring, you increase the elastic potential energy stored in the spring. And then when you release the spring, it bounces back, it springs back to its original shape. Make sure that you've marked and corrected your work, and then we'll move on in the video. So we're now going to look at this concept of internal energy. So to start, I want you to imagine that you have a beaker, and inside that beaker is some ice. So these are blocks of ice in my beaker. And I now put that beaker of ice onto a Bunsen flame, and I put a thermometer inside my beaker of ice to see what happens to the temperature of the ice. What we're going to do is measure the temperature every 30 seconds, and we're going to plot a graph. So on the x-axis, we're going to have time. On the y-axis, we're going to have temperature. What are the units of time in physics? Say your answer to the video. Seconds. And what are the units of temperature in physics? Say your answer to the video. Degrees Celsius. So what I'd like you to do is pause the video and sketch a prediction. What do you think the shape of the graph will be? Press play once you've done that. You should have now made a prediction of what you think the shape of this graph will be as we heat the ice. Now, most of the time, the predictions that I see are that the temperature will go up, something like, one sec, something like this, like a straight line going up. Sometimes people think it will be a straight line going up, but will then start to flatten out for various reasons. Sometimes people even think that it will get hotter and hotter at an increasing rate. Those are the usual kind of things that I see when people make this prediction. Now, what we actually see is that at first, so let's say the ice starts at 0 degrees. No, let's start even colder. Let's start at -10 degrees. So at first, the temperature goes up, just as you'd expect. You're heating it. What's happening here is you are applying heat. You are transferring heat energy to those blocks of ice. So it makes sense that the temperature goes up. And the temperature goes up and it goes up and it goes up. But at a certain point, the temperature stops going up. It's quite strange. Whenever I do this practical in class, people always say, "Sir, the thermometer's not working anymore," because they are a bit confused about why the temperature stops going up. You're heating it. The Bunsen burner does not go off at any point. I'm actually going to add that to the x-axis. Bunsen burner on. Heat being added. The whole time heat is being added, the Bunsen burner is on. Yeah, at a certain point, the temperature stops going up. And then it carries on going up again, which makes sense again. But then again, at a certain point, it stops going up. And then again, the temperature carries on going up. So in those sections where the temperature goes up, it makes sense. You're adding heat to the ice. You are heating the ice with a Bunsen burner. It makes sense that the temperature goes up. But it's these sections here that seem odd. Why does the temperature stop going up in those sections? Now, those points where the temperature stops going up are actually special points. This is ice. So these two temperatures should be familiar to you. What is this temperature over here? This 0 temperature for water? Say your answer to the video. So 0 degrees Celsius is the melting point of water. And what is this 100 degrees Celsius for water? Say your answer to the video. 100 degrees Celsius is the boiling point of water. So these seem to be special points. This is the melting point and the boiling point. So what happens is, if I label each of these sections, I'm going to call this section A, this section B, this section C, this section D, and this section E. In section A, it's a solid. It's solid ice, and it just heats up. Its temperature increases. In section B, it melts. It turns from a solid into a liquid. While it's melting, the temperature does not go up. I'm going to write that here. No increase in temperature, which is the strange thing. Section C, it's now a liquid, and its temperature increases, which makes sense again. In section D, it boils, and again, the strange thing happens. No increase in temperature. And then in section E, it's a gas, and it carries on increasing in temperature. Now, what I want to do is explain this. Why is it that when you heat a substance, and we've got the Bunsen burner on the whole time, why is it that at certain points the temperature increases and at certain points it does not? So the way that we're going to do that is by zooming in into the ice and actually looking at the particles inside. So the first thing I'm going to do is look at the particles inside the ice. So we're going to zoom in. We're going to look at the particles inside the ice. So we're going to start with ice at -10 degrees Celsius. And I'm going to have, let's say, 4 particles. So here are my 4 ice particles. And they're bonded together by forces of attraction. I'm drawing those as springs. We'll talk about that more later. They're not really springs. The forces of attraction are not really springs. This is just a model to help us understand what's going on. So those are my 4 ice particles at -10 degrees. And then I'm going to do my ice particles at -5 degrees. So that's slightly hotter. They're still bonded together in the same way. Now, those particles vibrate on the spot because these are the particles in a solid. So these particles are all vibrating on the spot. But those vibrations on the spot are bigger for the particles at -5 degrees. So at a higher temperature, the particles move, in the case of a solid, vibrate faster. What does that mean about their kinetic energy? Say your answer to the video. Their kinetic energy is higher. So at a higher temperature, the kinetic energy of the particles in a substance is higher. The particles move faster. We can look at a gas as well. So let's say we have a gas. So here the particles won't be joined together. So over here, I'm going to do a gas. So we've got, let's say, 3 particles. And let's say that's my gas at 120 degrees. And then let's say I now do my gas at 150 degrees. So again, we've got the same 3 particles. So these particles are moving randomly in different directions because these are the particles in a gas. And maybe they're moving at different speeds in different directions. But in the gas, the average speed will be higher. Those arrows on average are bigger. So in the gas, we have a higher average speed when the temperature is higher, and therefore a higher average kinetic energy. Notice this word average, because in a gas and also in a liquid And also in a solid, not every single particle has exactly the same kinetic energy. But if you find the average kinetic energy is higher in a hotter substance. So there is a link between the temperature of a substance and the average kinetic energy of the particles. So I'm going to write that as a final sentence. As the temperature of a substance increases, the average speed of the particles increases, and therefore the average kinetic energy of the particles increases. Note, in a solid, the particles are vibrating on the spot, but their vibration also increases as temperature increases, and their average kinetic energy does increase as the temperature increases. Even though they're not moving like in a liquid or a gas where they can move around, the particles still have a higher kinetic energy. They just vibrate more on the spot, as per my diagram over here. So please pause the video to copy this crucial sentence down. Press play once you've done that. You should have now written that crucial sentence down. So what we've said is, if you heat ice by constantly pouring heat energy into it, the temperature increases, but at a certain point, the temperature stops increasing. And then the temperature increases again, and at a certain point, the temperature stops increasing again. And I said that it was strange that even though we're pouring heat energy into the substance, the temperature doesn't increase the whole time. And to explain that, the first thing that we've done is we've looked at the link between the kinetic energy of the particles in a substance and the temperature of the substance. The higher the average kinetic energy of the particles, the higher the temperature of the substance. That works the other way as well. If you cool a substance down, so if the temperature of a substance decreases, what happens to the average kinetic energy of the particles? Say your answer to the video. So if the temperature of a substance decreases, the average kinetic energy of the particles in the substance also decreases. There's more to the explanation. That's just the first part. So please pause the video to do these questions. Press play once you've done them. You should have now done these questions. Please mark and correct as I go through them. So when a substance is heated, what two different changes can happen to it? So the first is that the temperature can increase. And the second is that a state change can happen. And the two state changes that can happen when something is heated is melting or boiling. Question 2, what happens to a substance when the kinetic energy of the particles inside is increased? Well, that's not going to cause a state change. That's going to make the temperature increase. That's what we've done so far. So the temperature increases. What happens to a substance when the particles inside move slower? So if they move slower, that's a lower kinetic energy. So the temperature decreases. 2 glasses of water, one at 25 degrees, one at 75 degrees. So comparing the motion and average kinetic energy of the particles. So the particles inside the 75°C water will move faster and have a higher kinetic energy than the particles inside the 25°C water. So the higher temperature water has more energetic particles, faster moving particles inside. Question 5. The average kinetic energy is going to be the same because they're both at the same temperature. But the total kinetic energy is going to be bigger in the bathtub of water because the bathtub of water contains more water. So even though the average kinetic energy of the particles will be the same, there's loads more particles in the bathtub, so the total kinetic energy of the particles will be bigger. That doesn't affect the temperature, but it is true. So the total kinetic energy in the bathtub water is bigger than the total kinetic energy of the particles, I should say, because I'm not talking about the water itself, I'm talking about the particles inside. The total kinetic energy of the particles in the normal small glass of water. Finally, question 6, in which state of matter is the kinetic energy of particles the least? So that will be the coldest state of matter, which is for any substance, the solid form. Please pause the video to mark and correct your work fully. Press play once you've done that. You should have now marked and corrected your work fully. So we're now going to move on to continue our explanation of why at a certain point the temperature stops increasing when we heat up a substance. So now we're going to continue with our explanation of why, as you heat a substance, it doesn't increase in temperature non-stop. At a certain point, it stops increasing in temperature. So the way that we do this is we imagine the forces between particles to be little springs. They're not actually springs, but this is a really good way of understanding what's happening. It's a scientific model to help us understand. So if I have two particles, and they are held together by a force, we're going to model that force as a spring. What do I need to do to pull those two particles further apart? Say your answer to the video. So to pull those two particles further apart, I need to put energy in. So to get those two particles to be further apart, I need to stretch that spring. So this spring is now stretched. To do that, I need to put energy in. Now, to get those particles to move closer together again, I don't actually need to do anything. If this was actually a spring and I just let go, those particles would just spring back to their original position. So the same with the particles inside a substance. For those particles to go back to their original separation, we don't actually need to put any energy in. In fact, we get energy out. And we call this type of energy potential energy. So initially, when those particles are close together, they have a low potential energy. When those particles are further apart and the spring is stretched, they have high potential energy. What that means is they have a potential to do something because they will snap back to their original positions. So there is the potential for that snapping back to happen. That's high potential energy. And then when they go back to being closer again, that's low potential energy. So this is the model that we're going to use to understand what's going on here. Particles inside a substance have both kinetic energy and potential energy at the same time. So if I draw a network of particles all bonded together by these forces of attraction, which I'm going to model as springs, all of those particles have both kinetic energy and potential energy. So they're also moving on the spot. So I'll do these little vibration lines to show you that. So they're moving on the spot, they have kinetic energy as well. These particles have potential energy and kinetic energy. And what that means is when you are heating a substance, so this is our graph from before, you heat the substance, the kinetic energy goes up and up and up and up and up. At a certain point, the kinetic energy stops going up and instead the potential energy goes up. At that point, which we said was melting, at that point on the graph, when the substance melts, the potential energy is increasing because the particles are being pulled further apart from each other. In fact, those forces between the particles are changing because between a solid and a liquid, in a liquid, the particles can actually start moving over each other. Then, once the substance is fully melted, the temperature increases again, so the kinetic energy of the particles increases again. And then at this point over here, when boiling happens, the temperature stops increasing because now the potential energy is increasing. The bonds are being broken even more so that the substance can become a gas. And then the temperature starts increasing again. So let's just go through that one more time. In this section over here, this first section, which I'll call A, what is increasing? The kinetic energy or the potential energy of the particles? Say your answer to the video. In section A, the kinetic energy of the particles is increasing because the temperature is increasing. So the average kinetic energy of the particles is increasing. In section B, what's increasing, the kinetic energy of the particles or the potential energy? Say your answer to the video. In section B, the potential energy of the particles is increasing. So the kinetic energy stops increasing and the potential energy increases instead. And that's what causes the solid to turn into a liquid. Let's call this section C. In section C, what's increasing, the kinetic energy or the potential energy of the particles? Say your answer to the video. In section C, it's the average kinetic energy of the particles that's increasing because the temperature is going up. In section D, what's happening? Is it the kinetic energy or the potential energy which is increasing? Say your answer to the video. In section D, it's the potential energy which is increasing. So instead of the kinetic energy of the particles increasing, which means the temperature would go up, the state is changing from liquid to gas. And finally, in section E, what's happening? Is it the kinetic energy or the potential energy increasing? Say your answer to the video. So in section E, it's the kinetic energy of the particles that's increasing. So what we've done here is we've linked kinetic energy to temperature. So the kinetic energy of the particles links to the temperature of the substance. And we've linked potential energy to state. So the potential energy of the particles leads to the state of the substance, which means as we heat a substance, remember on this graph, we're heating it the whole time. As we go along this graph, the kinetic energy of the particles increases, kinetic energy of the particles increases. At this point, the kinetic energy stops increasing and the potential energy of the particles increases as the state change happens. Then temperature increases, average kinetic energy of particles increases, temperature increases, average kinetic energy of particles increases. That stops. And at this point, the temperature stops increasing, the kinetic energy stops increasing, and the potential energy increases instead for the state change to happen. And then once it's a gas, kinetic energy of particles increases again. So at any point, you either have the kinetic energy of the particles increasing or the potential energy of the particles increasing, not both at the same time. When the average kinetic energy of the particles increases, that makes the temperature go up. And when the potential energy of the particles increases, that makes the state change. Now we have an overall definition for this thing called internal energy. Internal energy is the total kinetic energy and potential energy of all the particles in a substance. So what that means is, when I was heating this substance, I was at all times increasing the internal energy of the substance. At no point did the internal energy of the substance stop increasing. So now we can answer that question. How come in these sections here, temperature stopped increasing? The question we could ask is, where did the energy go? Well, instead of the energy going to the kinetic energy of the particles, the kinetic energy, the heat energy went to the potential energy of the particles. That's all that was happening. So in section A, the heat energy that I was pouring in increased the internal energy to increase the kinetic energy. In section B, the heat energy that I was pouring in increased the internal energy, but to increase the potential energy, which made the bonds weaken so that the particles in the liquid could move. In section C, I increased the internal energy, which increased the kinetic energy. In section D, I increased the internal energy, but that increased the potential energy, which made the bonds break completely, so the particles could now move freely, like in a gas. And finally, in section E, I increased the internal energy, so the kinetic energy increased. So at all times, as I was heating this, the internal energy was increasing. And that explains how there could be these sections where the temperature stopped increasing. The energy was still increasing, the internal energy was still increasing, but it was the potential energy increasing instead of the kinetic energy increasing. So at any point, either the kinetic energy increases, so that would be the temperature going up, or the potential energy increases, that would be a state change happening. So please pause the video to write down this definition of internal energy. Press play once you've done that. You should have now written down this definition of internal energy. Pause the video to do these questions. Press play once you've done them. You should have now done these questions. I'm going to go through them. You should mark and correct as I go through them. So the two state changes that can happen when a substance is heated are melting and boiling, depending on if you're at the melting point or the boiling point. When a state change occurs, that's the potential energy which is increasing. The kinetic energy would be a temperature change. Why does the temperature stop increasing even though the substance is still being heated? Well, it's the potential energy increasing instead. So you can say that the potential energy is increasing. The particles are being moved further apart. The forces between the particles are being weakened. Any of those would be acceptable answers. All three is best, so please add any that you've not written. At the boiling point, the temperature stops increasing even though the substance is still being heated. So that's going to be exactly the same as the answer to question 9, except rather than saying the forces between particles are being weakened, you'd say the forces between the particles are being broken, because in the gas form, there's no forces anymore between the particles. Question 11, which is increasing at all times? That's the internal energy. Question 12, when the kinetic energy decreases, what measurable change will take place? Well, kinetic energy links to temperature, so the temperature will decrease. And when the potential energy decreases, what observable change will take place? Well, that will be a state change. And if it's decreasing, that means it's being cooled down. So that's going to be either condensing if you're at the boiling point, or freezing if you're at the melting point. Please pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. So let's tie everything together. So what I'm going to do now is just stress the idea that we have the particles in the substance, but then we have the substance as a whole. So if we think about the definition of internal energy, so what is the definition of internal energy? Say your answer to the video. So internal energy is the total kinetic energy and potential energy of all the particles in a substance. All the particles in a substance. Now, we've linked the kinetic energy of the particles, or the average kinetic energy of the particles, to the temperature of the substance. So the higher the average kinetic energy of the particles inside, the higher the temperature of the substance. So we've got the particles inside, which have their kinetic energy, that's their movement. And then we have the substance as a whole. So think about the ice in the cup, and the temperature is measuring, that's a thermometer measuring the temperature. Two different things. You, the observer, always measure the properties of the substance. So you would measure temperature with a thermometer. So let's put a scale on the side to show it's the thermometer. And that's the ice inside. You measure temperature. You do not measure average kinetic energy of particles. You can't see the particles, but they are there and they do have a kinetic energy. And that's what gives the substance its temperature. And then we talked about the potential energy of the particles, and we discussed how that gives the substance its state. And if the potential energy of the particles increases, the state will change. So we have the potential energy of the particles, which is these forces between the particles, which we imagined as being springs. Remember, they're not springs, but we imagine them to be springs just to try and understand what was going on. And that's, if that potential energy were to increase, the ice would turn into water, so we'd get liquid water instead. So you, the observer, would see a state change. That's what you would observe. But what's happening is the potential energy of the particles is increasing. You wouldn't be able to see that. So I'm just stressing here that the properties of the particles links to the properties of the substance. Don't get confused between the two. The particles do not have a temperature. They have a kinetic energy. The particles do not have a state. They have a potential energy. It's the substance itself which has a temperature, which has a state. not the particles. It's a really common mistake people make when they say the particles have temperature. They do not. The particles have kinetic energy, the substance has a temperature. The particles have a potential energy, the substance has a state. So for example, in water, the particles in water have a kinetic energy, the water has a temperature. The particles in the water have a potential energy, the water has a state, which is liquid if it's water. So linked to that, there's a few things to discuss. The first is, what if I were to get my beaker of, let's say, water, so here's my beaker of water, and I were to move the beaker of water, so I move the beaker of water over there. By doing that, I've increased the kinetic energy of the water. Have I increased the internal energy of the water? Say your answer to the video. No, I have not. I've increased the kinetic energy of the water, not of the particles inside the water. So by moving a substance around, you increase the kinetic energy of the substance, but you don't increase the kinetic energy of the particles inside. So you do not increase the internal energy. Another thing I could do, I could take my cup of water and I could move it up, thereby increasing what form of energy? Say your answer to the video. I've increased the gravitational potential energy of the water. Does that increase the internal energy of the water? Say your answer to the video. No, it does not. If I've increased the gravitational potential energy of the water, I've not increased the potential energy of the particles inside. So I've not increased the internal energy. So don't get confused between the substance and the particles inside. If I increase the kinetic energy or the gravitational potential energy of the substance, that does not increase the internal energy. That does not increase the kinetic energy and the potential energy of the particles inside. Another thing I want to discuss is, what if I have, for example, a big block of ice? Here is a big block of ice. And then I cut that big block of ice into some smaller pieces of ice without changing the temperature. How does the internal energy of this smaller piece of ice compare with this bigger piece of ice? What do you think? Say your answer to the video. Well, the internal energy of A, so the internal energy of A is actually bigger, no it's not, it's actually smaller than the internal energy of B. Even though they're both at the same temperature, which means the particles inside have the same average kinetic energy, the total kinetic energy of the particles in the big block of ice is going to be bigger. There's more ice in B. B, there's more of it. A, there's less of it. So B is going to have more particles and therefore more total kinetic energy, therefore more internal energy. Piece B, piece A is smaller. It's got less particles. Those particles have the same average kinetic energy, but it's smaller, so it's got less internal energy. Linked to that, let's have a look at a really big swimming pool of water. So that's a swimming pool. And that swimming pool of water is at 30 degrees Celsius. And then I have a tiny cup of coffee. So I'm trying to draw this to scale. It's probably not. That's probably a really big cup of coffee if this was to scale. But that's a cup of coffee. And it's at 80 degrees. So swimming pool of water at 30 degrees, cup of coffee at 80 degrees. What I'd like you to do first is compare the average kinetic energy of the particles in the swimming pool to the cup of coffee. Pause the video, write down what you think, press play once you're ready. So the average kinetic energy of the particles in the coffee is bigger than the average kinetic energy of the particles in the swimming pool, because the temperature of the coffee is bigger than the temperature of the swimming pool. But what I'd like you to now do is compare the internal energy of the swimming pool to the cup of coffee. Pause the video while you do that, press play once you're ready. So you should have now compared the internal energy of the two. The internal energy of the pool is actually bigger than the internal energy of the coffee, because internal energy is the total kinetic energy and potential energy of all the particles. In the swimming pool, there are way more particles. Yes, each particle might have less kinetic energy than in the coffee, but there's way more of them. So even though each particle has a smaller kinetic energy, there's way more. So the total kinetic energy of all the particles in the swimming pool is going to be bigger than the total kinetic energy of all the particles in the coffee. So the internal energy of the particles in the pool is bigger than the internal energy of the coffee. Please pause the video to do these questions. Press play once you've done them. Should have now done these questions. I'm going to go through them. Please mark and correct as I go through them. So how does the internal energy of each half compare to the original internal energy of the whole? So the internal energy of each half is going to be less than the internal energy of the whole, it's less particles. The average kinetic energy, well, it's still the same ice, so the average kinetic energy will be the same for both because they're both at the same temperature. The only one in question 15 which will increase the internal energy is heating it. Lifting it up will increase the gravitational potential energy of the whole block of ice, not of the particles inside. Accelerating it will increase the kinetic energy of the block of ice, not of the particles inside. So the only thing that will increase the internal energy is heating it. Which contains more internal energy? Well, it will be the bathtub, because even though the average kinetic energy of the particles is smaller in the bathtub, because the temperature of the water in the bathtub is lower, the bathtub contains a lot more water, so the total kinetic energy will be bigger. And finally, define internal energy. That's probably going to be the most common question you can get asked. It's the total, let's write it fully, kinetic energy and potential energy of all the particles in a substance. You could also say sum instead of total. And that's that. So what we've done is we've talked about how everything has internal energy, and when you heat something up, or even when you cool something down, you can change its internal energy. So when you heat something up, you increase its internal energy. When you cool something down, you decrease its internal energy. But that can either affect the temperature, which is linked to the average kinetic energy of the particles, or it can affect the state, which is to do with the potential energy of the particles. I hope this video was useful. Please like and subscribe for more videos on GCSE physics.